Alrighty guys, we're talking about waves today. Yes. We'll talk about that later. So we've got, this shows us a transverse wave. Of course there are different types of waves. And what we'll talk about today are mechanical waves, which require a medium to exist. And we'll kind of showcase waves on a slinky. Super fun stuff there. So let's talk about the main difference between the transverse and the longitudinal wave. First, Wesley would like to be my assistant. Excellent. All right, so hold that slinky, stand over there. Cool. Step back a couple feet. There you go, boom. All right, so here's our slinky. So the main difference between the transverse and the longitudinal wave here is the direction of the particle's displacement. Okay, so before we get there, we have to understand that a wave is a displacement of matter, but it really doesn't actually carry matter from one place to another. We're not talking about surfing and the surface waves. That's completely different. But if we think about the water is just displaced temporarily. Just like if we have like a crowd wave. Okay, so a group of people, they stand up and then they sit down, and then the action of them standing up and doing this special thing kind of induces the next people to do that as well, which is really kind of how waves work, is that waves are a propagation of displacement. So as I displace one part of the slinky, it makes the next part of the slinky want to do the same thing, and the next part, and the next part, and the next part. So the wave will travel through matter because one particle, or groups of them, will induce the next ones, like right next to each other, to do the same thing. So when we talk about the motion of the matter, so the wave isn't so the wave on the slinky isn't actually moving the slinky around to a different location. It's temporarily displacing parts of the slinky, but as the wave acts on a piece of slinky, after it's gone, the slinky pieces are still there. So it only displaces it for a short amount of time. After the wave is done doing its thing, then the things are still there. Okay, so in terms of the transverse wave, we see that the motion of the particles are perpendicular to the direction of the wave motion. So you'll see the wave traveling down the slinky and then back. We'll talk about the reflection here in just a minute. But watch what happens to the displacement where the slinky pieces are actually going. So I'm going to kind of whip it to the left here, kind of like that. And although it's kind of small, well, I had a bigger slinky, but somebody in Mr. Sensei's class broke it. So, but we are working on getting another long one so that we can do this better. Your sister's at the door. Can you let her in? So, again, when I whip it sideways, the particles of the slinky move sideways, but the speed of the wave, or the wave direction, is going down and back through the slinky. So this is a transverse wave. The particles are moving perpendicular to the direction of the wave motion. So this is what we see here, because a transverse wave is more easily drawn than a longitudinal wave, which is what we have up next, as in if we were to compress the slinky. No, don't move. Don't move. Keep it tight. So I'm letting the compression go down. So as you track and see what's happening with the motion of the particles, they're moving in the same direction as the direction of the wave itself. So this is a longitudinal wave. Sound happens to be a longitudinal wave as well. Thank you, sir. Appreciate it. All right, so now we covered the basics. We also should know parts of the wave as well. Like if we wanted to look at B and F, those are what kind of points?
Maximum.
Maximum, but for waves we have a special name, starts with a C. It's also the name of toothpaste.
Crest.
Crest. There we go. Oh, you guys say cold. Okay. Yeah, crest, like the crest of a wave. It's the high point.
Wait, what did y'all say?
Colgate.
It's not a good.
I mean, it is a toothpaste brand.
Okay.
Not also a toothpaste brand, but what do we call point D?
Trough.
A trough. Yes, like a pig trough. They eat out of the trough. It's the low point because they're low to the ground. If we so imagine this is like a string, right? And waves are on the string. If the string had no waves on it at all, it would lie along this central axis line here. And then if we were to measure the distance between where the string was before and up to the crest or down to the trough, what do we call those?
Amplitude. Wait,
Say it again.
is it amplitude?
The distance between where it was before and its maximum displacement, either up or down. Amplitude, yeah.
Amplitude, okay.
Same thing from oscillations. In fact, isn't it true that we need an oscillation to produce a wave?
Yes.
Yes. So things like frequency and period are also crossover concepts into waves as well. But something new, we have the concept of a wavelength. Okay, so this is kind of like the period, where the period is the time for one full cycle of an oscillation, but it also works for waves. But the wavelength is going to be the length of one full cycle
Did you
of a
put
wave.
beef?
As in,
Okay.
if, so you saw me send a single wave pulse down the slinky. Okay?
Okay.
But this is more like if I were to continue making waves, if I were to continue moving my hand up and down, making a continuous or a periodic wave, that's what we're talking about, because we see many cycles and we can look at that aspect as well. So we can do this a couple of different ways. First off, to be more specific, even though there are no axes on here, technically this is a displacement position graph, and we can see something like that. Okay, as a periodic wave. Excuse me.
Bless you.
Thank you. I knew it was coming.
I hate that feeling.
Yeah, wavelength. So, if we're talking about the length of one full cycle of a wave, it's going to be, well, one of the ways that we can measure it is from one crest to the next crest. We call this the wavelength. That's a Greek letter lambda. It's small lambda, and it stands for wavelength. So the length of one full cycle of a wave, so from crest to crest, or we can measure from trough to the next trough. That would also be good as well. Or there's a third option. If we were to start at any particular point, but let's say that we start here, okay, and we wanted to find what is the wavelength of the wave, then I would need to get to the same position as it was before, okay? So if I would go from here to here, so it's at the same position, but it's not the same place in the cycle though, okay? Because at this point, like we're going up and we're at the same position, but now we're going down. I gotta keep on going until it completes the cycle. So from there to there would also be a wavelength. So on our graph here, okay, so there's actually three different ways that we can express the wavelength, okay? If I can see her, yes, we can let her in. I see her. Hi, Bruce.
CG.
Thank you. So of our answer choices, we have from crest to crest, BF is the proper answer for our Bellward question. But what other two choices would also work if this were a right in?
A, E, and CG.
A to E, that is correct, that's one full cycle, and C to G, also correct, one full cycle. Good, good, all right. So, but officially B is the correct answer for our bell work, so let me record those points, and then we'll be on our way. I will need to start the test for those of you who missed it last class. If you can, so let's see, Martin, Jordan Edwards, Kai, who's not here, Abraham, who's not here, and Ashok. So if you guys are ready to take the test, that'll start here in just a few minutes.
Oh, God damn.
Okay? Alright, so let's take a look and see here. Looks like everybody got B eventually here. So there we go. 1, 2, 3, 4, 5, 6, 7. Excellent. Alright, so give me just a minute. I'm gonna reopen that test for our makeup test takers, and then we'll be on our way.
What would you get first?
Has he not put it in yet?
He put it in.
Oh, he put it in.
By the way, I do know that that was a particularly low scoring test. We may have some time in class where we go over the test questions, but the makeup tests have to be completed first before we do that, obviously. I did make a new review guide. They are in the copiers right now, so I will get those to you whenever those are ready, so that you have more practice as you head towards the retest, which should be taken in a couple weeks. Definitely before the end of the third 9 weeks, I'll give you a chance in class to take that retest, but we may also spend some time in class going over some additional topics, or maybe even some of the test questions as well. Okay, so don't worry, I got you. I've got more resources and opportunities to improve your grades, so hope is not lost. All right.
This is like SL we're learning basically, right?
¿Qué pasa?
At this point, it's SL.
Well, at this point, because I don't know who's going SL and who's going HL for next year, so everything that we learn right now, even though it may be additional HL topics, we're all learning it until next year, where we know for sure who's SL, who's HL, and then we can do more of like, well, whenever we have an SL lesson, whenever we have an HL lesson, the SLs can take a break, that sort of thing. So next year, SLs will not be responsible for learning HL stuff, but as of right now, you do. So, like all of the A4 chapter, like the torque and the rotational stuff, that's actually HL stuff. But it's part of the AP Physics 1 exam, so that's why we learned it all this year. To be fair, the chapter that we just tested on, the electric and the magnetic fields, the waves that we're doing this time, and then and after spring break, we've got one more chapter to talk about circuits. Those three are not on the AP exam, but those will help us for next year in IB. So, yes, and I know my IB sophomores, you guys had some meetings this morning, so you might have some more questions. We'll definitely have some time after our lesson if you have more questions on those things. Okay? Sweet. So let me get back to this. All right. All right. So my makeup testers, feel free to log on and
My first period teacher
get started with that. You'll definitely need your equation sheets.
and she came back in like sobbing. And
Oh, cool.
we don't,
Yeah.
I don't know why.
And
Who's your calculus teacher?
Martin needs one.
You're in the
No, that's what I was asking you. Like, how do you know?
is Miss.
No, how do you know?
That's my homework. Yeah.
okay, let's get back to business. Okay, since we're on a pause here, I did post on Rooms my official recommendations about AP prep books for the AP Physics 1. So it's either the Princeton Review or Barron's. The 5 steps to a 5, apparently it was on pre-order. It was supposed to be shipped out like yesterday, and now it says it won't ship out till August.
What?
Yeah, so they're not selling any of their books this year, apparently. Yeah, so of the 4 that you guys bought for me, and I thank you so much for that, these are the best 2. They are not perfect, but I do list some pros and cons on the post, so feel free to read that, and then you can go shopping and see which one you want to get. I mean, technically you could get both if you wanted to. You don't have to get these. When it comes time to review, I'll try to have some paper copies of things, some practice exams and things like that, so that if you don't have a prep book, then you'll still be able to do some good review. So you don't necessarily need to buy a prep book, but it would help to have your own copy so that you can go through your own and you can write in, yourself and all of that stuff, jazz. But yeah, so Barron's or Princeton, make sure to look at the post and see what I say are the pros and cons of having those. So, because both are not perfect, but they're pretty close. Yes?
There isn't a new test.
Yeah. Huh?
There's no test for us.
What they say.
Are you looking on Teams?
Yeah.
That's where I usually post.
Yes.
It just says it just shows the one on Friday.
Yeah, do that one.
And that one
Yeah,
does
it
not
doesn't work.
It says
Whenever
no more tests.
This form is currently not accepting responses.
Yeah, what they say.
This is a.
Oh.
That's pretty funny.
Wow. Yeah, I think that's your phone.
Try now.
Okay. That's happened to me with timers and clocks. I get woken up. Okay, let's see.
So, are we good now? All right. Huzzah! 1, 2. Who's my third one? Martin? Oh, yeah, you're still getting it.
It still doesn't show it for me.
What's up?
It just still doesn't show it for me.
It still doesn't show what?
I refreshed it.
Like, and you clicked on that link?
Well, that was on. Oh, really?
Yeah.
Okay,
There you
there you go. Okay,
Cool.
thank you.
Nah, but it's something perfect.
Okie dokie. All right, let's keep rolling with waves. Let's see, what else do we need to talk about? So this actually is a pretty chill lesson. The concepts, there are many of them, but they're all very low level. Of course, this is the first of many lessons that we'll talk about waves. So we start with those basic ones here. So before we get to our next equation, we are in the C2 section of our equation sheets. So we did the C1 already, that was our oscillations. So then our C2 is on waves. And there's only one equation for here. We already talked about how waves will travel through space with a certain speed, and technically we can use our basic speed equation, distance over time, but there is another specific to waves, wave speed equation, which is given to us in our equation sheet. So the speed of the wave is equal to the frequency times the wavelength. We have that wavelength lambda again. Remember also the frequency and period are inverses of each other. We learned that in our C1, it's right up there. So they actually give you this same expression in terms of the period as well. So here is our wave speed equation. It is important to note that what changes the speed of the wave? Okay, so Jordan, can you help me out this time? All right, so Jordan's going to help. So she's gonna hold, and so we're going to observe how fast the wave goes down the slinky. Okay, so I'm gonna whip it kind of like a normal, and so it takes about a second to get down there. Okay, roughly. We'll talk about the reflections and stuff later on. Now, if I were to whip it faster, okay, or slower.
You're just making the wavelength bigger.
So, yeah, so I'm not actually changing the wave speed. The speed is staying constant, even though I may do it quickly or not so quickly. Even with the amplitude, if I do it just a little bit, or if I do it a lot, it's the same speed. So I cannot change the speed of the wave by the source of the waves, okay? But what if we stretch it out a little bit, okay? Okay. Do not do this at home and let go, because that's how you break a slinky. That's how the other one got broken too. Anyway, so now observe how fast it's going. Takes about the same amount of time, doesn't it? But now it's covering more distance. So more distance in the same amount of time tells us that we're going faster. And what did I do? I stretched out the slinky. Okay, I changed the property of the medium that the waves are going through. That's what controls our speed. Okay, not how I make the waves, but it's the properties of the material itself. That's what changes or is responsible for the speed. Okay, so if I were to stretch it out, I change its speed. If I switch it out for a plastic slinky, I would change its speed. If I found a heavier slinky, I would change its speed. Okay, so it's the properties of the medium is going to be what determines the speed of the waves that go through it. But how I move it, so I can change the frequency or the wavelength or the amplitude. But all of those things do not affect the wave speed, even though the frequency times the wavelength will equal your wave speed. Your wave speed does not change based on if these guys change. Okay, it's just based on the medium that it's in. So, we saw this particular graph, but there is another type of graph that you might see with waves, which is kind of what we saw before with oscillations, is if we had a displacement time graph, and they might look very similar to each other, okay? But the units, of course, this would be like in meters, and this time, that would, of course, be in seconds. So this is a displacement position graph, where we have the wavelength is equal to 1 full cycle of the wave. But in the displacement time graph, if we did that same thing, that doesn't stand for wavelength. What does that stand for? Almost. Invert that.
Period.
The period, yeah. It's the time for one complete cycle, or one complete wave. So this is going to be the period. So based on what kind of graph we have, if it's a position, if it's a displacement position graph, or a displacement time graph, we can get either the wavelength or the period by doing the same exact thing with the graph, finding out how much is one full cycle. Okay, so let's take a look at our challenge question here. Sean,
I'll change it.
this came for you the other day that you were asking. You're welcome. Buzz, buzz.
Okay, I'll do the door first. You know what?
All right, buzz buzz. Looks like a popular answer. I'm gonna call it done in 3,
Wait.
2,
After this, we'll be at 40.
1. Done. All right, lots of bees, buzz buzz. Here we go. So, we're solving for the frequency of this traveling wave. We are given the speed, 50 meters per second. Notice we have a displacement position graph. So if I were to find the full cycle here along the x-axis, that would give us the wavelength. Okay, the wavelength. So now I don't have a whole lot of numbers here, not too many tick marks. But if I were to track, so from the d-axis, we start here and we go one full cycle going up to about here. Looks like 10 meters for our wavelength. As we use our wave speed equation here, solving for the frequency, that's going to be the speed divided by the wavelength. 50 meters per second divided by 10 meters gives me 5 hertz. For our frequency, B is the correct answer. Good job, guys. Yes. All right, looks like Kwanzaa is taking first place, followed by Spice Girls in there for second, and the Spectrum taking that third place point.
No, we got 1 in the last one.
Excellent, excellent. Okay, let's take a look at another one. Here we go. Next down question. Just talked about this one too.
And you get this one 50, so 14. Well, I mean, when we stretch it out, it goes faster.
I should definitely get extra credit.
These are longer. Wait, no, you're right. Because when he did his, when he went longer, it went faster.
Definitely get both.
Just click the wrong.
You clicked the wrong one.
The click wrong key.
You mean this one? A displacement time graph. This was a displacement position graph. All right. Well, we got lots of E's here. Actually, all E's. I'm gonna call it done. 3, 2, 1, done. Okay. So which one of these would make a pulse travel faster down a stretched string? You guys didn't choose A or B. That is correct. Okay. Or that is a good not choice. It's good that you didn't choose A or B, because both A and B talk about the source of the waves, and we know that the speed of the waves depends on the medium. So we have to change something with the medium. Okay, so A and B are out. You guys all said E. Use a longer string of the same thickness, density, and tension. Longer string. Now, when we did the waves with the slinky, I made it longer, but as I made it longer, it increased the tension within it. Okay, so just because I have a longer something doesn't necessarily mean that the properties are changing. Okay, if I have a same string, that's the same thickness, same mass, same tension, it doesn't matter if it's a long or short string, the speed should be the same based on those factors alone. So unfortunately, it's not E. Okay, but which one should it be? Would a heavier string work or a lighter string work? Imagine if you go to the gym and you've got those big ropes, right? And you do the thing here. So the heavier ropes, one, they are more difficult to whip up and down, but also the waves will travel slower on the heavier ropes. They will travel faster on the lighter string. So D would actually be the correct answer here.
Oh,
Yeah.
what is this slinking exception? It went the same speed.
If so, so with the slinky, when we stretched it out, we increased the tension, and that would increase the speed as well if we were to do that same thing with the string.
So it's not even because it's the same tension.
Say that again.
It's not even because it's the same tension.
Correct.
No way, bro.
This for after school. Okay. Alright. Seniors. Gotta love it. Yes. 2 buses down, we're working on the 3rd one. Tracy's already has her spot. Huh? Fast? I was expecting a bit faster, but
What? Expect what?
the buses to fill a little faster, but traditionally we always have a big rush of students right at the last minute, which is not this weekend but next weekend. March 2nd is the last day to paper grab bash. Not that you guys know or care. You guys aren't seniors, not yet.
Can you tell who paid?
Can I tell who paid?
Yeah.
So I've been receiving printouts from the bookkeeper, but I do not have a live list. I got a printout this morning, so I can tell who's paid up to this morning. But yeah,
You wanna check and make sure my sister did?
I can check later. Yeah. Okay, cool. All right, let's take a look. I think superposition is next. Yes. Yes. Okay. So, so since waves are not actually matter, but rather they are displacements of matter, they're energy that moves through matter, we can have 2 waves at the same place at the same time.